Okay, my friends, so this right here is the simulator I built in Excel that's going to roll a die for you. The die is right here. It's currently showing a 3. And if you look at this little table here in columns F and H, it's showing you what has happened so far. So I reset the simulator from what it was in the previous section back to the first roll. So that 1 right here means that it's rolled 3 one time. I'm going to roll the die again, and that time it rolled a 1. So you're seeing that updated over here. The 3 that already happened is still being maintained here, but now it also rolled a 1. Let's roll it again. All right, it rolled a 3 a second time. Let's roll it again. It rolled a 1 a second time. That's kind of fun. It just rolled a 5 and a 2. So hopefully you can see what's going on now. It's just repeating the die over and over and over and over again and keeping track of what's going on. Now, over here, I'm going to open the window up a little bit here. This is a pie chart of the results of what we've seen so far. So far I've rolled 6 times, and you'll see that the percentages of the faces we've seen are showing up 16.67% for 5. That's that teal color up here in the top left corner. 33.33, that looks like the 1. 16.67, that's the that looks like 2s. And then 33.33 is 3s. It's going 1, 2, 3, 4 is the 0, 5 is the teal, and 6 is a 0 up here. Now next to that, I'm going to open the window up a little tiny bit more. This is the theoretical probabilities of rolling a die. They're not going to change because the theoretical probability of rolling any one of the faces of a die is 1 out of 6, so they're all 16.67. So you might notice that over here we've already established 16.67 on, what is that, 5 and 2. But what's interesting is we're double the probability we should be on 2 of the other ones, and we don't even have a probability yet. So this is all unfortunately due to a very, very small sample size. Let's roll again. See, now we just picked up, what did we just pick up? We picked up a 6. So now 6s are on the board. The probabilities are all screwed up. We've got another 3. Another 3. Man, see, it's so wild. These probabilities now are really not a whole lot, especially 3. 3 is really off. So let's keep rolling. Another 3. Half of the, oh my goodness, this is so fun. We've 10 rolls and half of them are 3s. So ridiculous. But again, this happens with experimental probability. You get these little random runs and clumps. So what I'm going to do is keep rolling. Aha, we just had a 4 show up. And I'm going to hold down this roll button and let it go. And watch what happens as I hold down the roll button, which means I'm rolling this die very, very, very quickly and repeatedly, and we're letting Excel keep track of the percentages as we go. Look, please notice what is happening to the experimental pie chart compared to the theoretical pie chart.
I do not suppose you could have split things up.
As you wish.
Okay, my friends, so we got about 4,400 trials-ish somewhere over here. How many total trials do we have? We've got 26,000, and that's a ton. It's actually a fairly small sample for a Monte Carlo randomizer, but I think you're getting the point. The percentages now, if we zoom in on just the percentages, experimental versus theoretical, you see that what's going on. I mean, as a matter of fact, if I took the labels off, I bet you couldn't even tell those two apart. They're that close. They are that close. And you can see the percentages. I mean, well, hell, 3. Remember 3? 3 was the problem child earlier. We had all those 3s in the very beginning, and now it's the only one that matches to 2 decimals, the theoretical. Now, none of them are that far off anymore. But again, what does far off mean? We can analyze these numerically, but the big idea is not to analyze them numerically. The big idea is to realize that after lots and lots and lots of trials, the experimental probabilities look an awful lot like the theoretical ones. Read on and see why.